This video is going to walk you through how to draw and label a seasons diagram, the two different versions that we have, the two different perspectives of diagrams that we have based on how we're seeing them from outer space. So the first one here, we've got a little model of the sun, the Earth, and you can see I've got the Earth tilted in a direction with the North Pole in the direction of the sun. If you recall from class, the northern pole always tilts in the same direction in outer space. It always tilts towards that north star called Polaris. Polaris would be somewhere way over here off the left-hand side of the screen. As Earth revolves around the sun, that north pole always remains tilted in the direction of Polaris. It's always going to be tilted in that same relative direction. So as we're revolving, keep that in mind, that the North Pole is always tilted in that direction. So on my paper, I've got a sun drawn here in the center. And around that sun, we're going to go ahead and draw 4 other circles that are going to represent the Earth at different times of the year. Now, remember, these diagrams are pretty bad because of the nature of trying to turn a 3-dimensional model into a 2-dimensional diagram. So for example, this circle up here is actually representing the Earth in this position. So we're looking at the Earth-Sun system from a perspective, and it's going to be drawn in a really terrible 2-dimensional perspective on our paper. This circle here would represent this location here, and this circle here would represent this location here. So please keep in mind that as we're drawing these diagrams, thinking 3-dimensionally about this 2-dimensional space that we have to draw with. So now that we've got that, I'm going to draw a star over here on the left-hand side of my paper, and I'm going to call it Polaris, just to remind me that all of my northern poles need to tilt in that direction. It's okay if your tilt is not quite 23.5 degrees. It's just a model. It's just a diagram so that we can understand the concept. And if you would like to add in some equators, you can do that. All right. So we're going to start with this diagram here, which represents the Earth in this position. If you notice, the northern pole is tilted in the direction of the sun, which means the most direct light is going to be hitting in the northern hemisphere at that 23.5 degree line, that Tropic of Cancer. So this day in time would be the northern hemisphere's summer solstice. This is the first official day of summer. It happens every year right around June 20th or so. And on this day, the most direct light is striking Earth at that 23.5 degree north latitude line, which means more energy is going to be absorbed in the northern hemisphere. It's going to be increasing the amount of energy in the atmosphere and creating warmer temperatures overall. As time moves on, so into July, into August, into September, we're going to draw an arrow counterclockwise around the sun always. So Earth always moves in a counterclockwise pattern. And we're going to label that line as a 3-month season. And that season is the summer season. So this is representing the very first day of summer. That is one day of the 365-day calendar. For 3 months approximately, we would be in the summer season until we get to the first day of fall. That first day of autumn is called the autumnal equinox. This happens every year right around September 22nd. And on the autumnal equinox, the most direct light is now going to be striking at the equator, or 0 degrees latitude. So you can think about it this way. On this date, we were getting the most direct light in the northern hemisphere that we'll get all year long. As Earth continues its orbit, that direct light starts to shift towards the equator. And as that happens, we're getting less and less and less and less direct light, which means our temperatures are going to be cooling down. The same is going to be true for the next 3-month period. And we'll call this 3-month period the autumnal season. Or, if you'd rather, you could call it the fall season. We call it fall because leaves are falling off the trees. This takes place at the end of September, all of October, all of November, and most of December. until we get to the first day of our official winter season. We call it the winter solstice. This happens usually right around December 20th every year. And on this date, the most direct light is now hitting the 23.5-degree south line, the Tropic of Capricorn. Because the most direct rays are now striking the southern hemisphere, that means the northern hemisphere is experiencing very little energy absorption, and it's going to be cooling our temperatures down. For the next 3 months, the next 3-month period, we're simply going to call winter season. So this is the end of December into January, all of February, and most of March until we hit our next milestone, which we call the vernal equinox. That is the first official day of the vernal season, or what we would typically call the spring season. This happens right around March 22nd each year. And because it's an equinox, we have our most direct light, again, hitting right about the equator, the 0-degree latitude mark. 3 months later, we get back to our summer solstice after our 3-month spring season. Or again, you could call it the vernal season, which is the actual name of it. This process repeats over and over and over again. So here's our summer solstice in our model. Here's our autumnal equinox. Here is our winter solstice. And here is our vernal equinox. And again, try to remember this is a 3-dimensional concept that we're drawing into 2-dimensional space. So our diagram is going to look a little funky compared to how the Earth is actually moving around the sun. At this point, what I'm going to do is I'm going to look at Earth's system from the opposite side of the solar system. So right now we're looking at the sun and the Earth this direction. I'm going to pretend that I'm walking around to the other side of the solar system and looking this direction. So instead of actually moving the camera, I'm simply going to move our system. Remember how Polaris was over here on our left? Well, now I'm going to put Polaris over here on our right, so that essentially imagine taking a rocket ship around the sun to the other side and peering into the solar system from the opposite direction. So that Polaris is no longer on your left, it's on your right, which means the summer solstice location is also going to be switched. So we're going to move the entire system around. We're going to rotate everything around to change our perspective. So we're going to move this over here, which means Polaris is now over here on our right. So let's flip our diagram over and start fresh. We are no longer looking at the solar system from the camera's perspective. We're looking at it from the opposite of what the camera would be seeing. So I've just moved our diagram, which means Polaris is on our right, sun is here, and we still need our 4 Earth diagrams. But now our tilt is in the other direction. It's towards Polaris. Remember, it's never changing. It's always tilting towards Polaris. But in our diagram, because we're looking at it from a different perspective, they're tilted in a different direction. So in this diagram, again, we can label this Polaris. Our summer solstice is happening in the same time, the same place where it was before. We're just viewing it from a different perspective. So instead of the summer solstice being on the right-hand side of our diagram, because the northern pole is tilted in the direction of Polaris, we're now going to see it on the left side of our diagram. So here's our summer solstice. And you'll notice North Pole is tilted towards Polaris and the sun. This happens again right around June 20th. Most direct light is at 23.5 degrees north. 3 months later, we get to our autumnal equinox. And remember, Earth is always moving counterclockwise around the sun. So the Earth is going to be doing this. All right. Autumnal equinox, most direct light hits at the equator, 0 degrees. And this happens right around September 22nd of each year. 3 months later is our winter solstice. This happens right around December 20th of each year. And the most direct light is hitting at 23.5 degrees south. So again, we're losing energy. We're not getting as much direct light. So the energy starts to decrease and it decreases our temperatures. About 3 months later, we get to our vernal equinox, the first day of our vernal season, our spring season. This happens right around March 22nd of each year. And again, it's an equinox. So we're going to be hitting the 0-degree latitude line with the most direct light. So our temperatures are now going to start increasing because the angle of light is being more steep this time of year. 3 months later, we get back to our summer solstice. Let's go back and label these times in between. So summer solstice happens here in the diagram, and for 3 months, we're going to have the summer season. And then we get to our first day of fall, and then we'll have our fall season. First day of winter, followed by 3 months of our winter season. First day of spring, and then 3 months of our spring season. Now what you should notice, what you should be able to do is actually pick your diagram up, look at Polaris here, and if you're looking at it in a light enough room, you should be able to see Polaris shining through the other side directly over here. Because again, we didn't change anything about the diagram, we changed our perspective. So Polaris stays in its location, and you can kind of see the sun shining through on the other side. The sun's in the center, Polaris is here. Here's our summer solstice location. Here's our summer solstice location. Again, this is just a perspective change. The diagram that we drew on this side is exactly the same as the diagram we drew on this side. It's just looking at it from a different perspective. So for example, here's our summer solstice. Polaris is over here. I could take the camera, and I'll do it really quickly here. If I take the camera and move it around to the other side of our solar system here, I didn't move the Earth. It's still in the summer solstice position. But now it looks like it's on the opposite side of the screen. Not because the Earth moved, not because the summer solstice is in a different position, but because I've actually changed my perspective. And that's the only difference between our two drawings, is the perspective. Let's try it again here. When we go to our summer solstice and we go counterclockwise, we've now found our autumnal equinox. Well, if we move our camera to the opposite side, it's still in the autumnal equinox position, but you'll notice it's in a different position relative to how we're viewing it. In this position, it looks like it's above the sun in our diagram, but in this position, it looks like it's below our sun in the diagram. It's the exact same location. I didn't move it. I just changed my perspective.